So re:Invent's coming to a close. Hope you guys have had fun. Good week. So I'm going to talk today about low latency multiplayer with AWS. So launching a game is a ton of fun, right? You spend a year or 2 or 3 of your life toiling away, crunching, trying to create this awesome experience. And you have a private beta, you have a public beta, you load test your servers, you make sure everything's hardened and ready to go. And then when it comes time to launch, there's still about a 50-50 chance that everything's going to just completely fall apart. Some of you have probably been through this firsthand. I have as well. Before coming to AWS, I spent many years at PlayStation building and launching online games. And luckily, many of them went well, but some of them did not. At least they were learning experiences. But this has really kind of become a pervasive problem for the game industry. Almost to the point where a lot of players expect a game to just be completely broken for weeks after any major release or new DLC, et cetera. So how do we actually fix this? How do we leverage services that AWS provides, leverage newer patterns in game servers in order to avoid falling into the same traps that people have fallen into time and time again? So by the end of this session, hope you leave with some real-world practical tips that you can take back when you're designing your next generation game backends. And then also just some philosophical decision points so that you more understand the process. Your game probably won't look exactly like any of the diagrams that I'm going to show, but the idea is to understand the process and the type of decisions that you need to make. And hopefully overcome issues like this. So I'm Nate Weiger. I run the gaming solutions team at AWS. A member of my team, Drew, is going to speak right after me about load testing. And then I'm joined today by James Gwertzman, the CEO of PlayFab, who has actually built a game platform that has powered several top 10 Steam games following principles such as these. So in order to make this more tangible, I kind of came up with the idea of walking through a hypothetical game. So this is just something I came up with. This Knights versus Samurai. The idea is this is going to be 4 versus 4 death match. You're just going to go on and hack your friends to bits. The people that hack their friends to bits the fastest win. Game that I personally would have a blast playing. This is a cool piece of artwork, actually, care of game artist Dan Scott. I found it on an image search. I emailed him. He's like, yeah, sure, cool, use it. So thanks, Dan. So with a game like this, obviously, low latency is going to be really important. But also, we want to make it a global experience. We want people to be able to log on and have equal opportunity to hack themselves to bits, whether or not they're in the US or Europe or South America or Japan, et cetera. So how do we resolve those two? Because they're inherently in conflict. Let's talk about latency to begin with. So this is a map care of Superdata Research that shows average latency around the globe. And the exact numbers, they aren't that important. I don't know exactly how accurate, but they're in the ballpark. The idea is when you're in a given region, your latency is good. If you have game servers in a given region, your latency is going to be fine. But anytime you're leaving that region and you're going across, the Pacific to go over to Japan or going across the Atlantic to get to Europe, you're adding 100, 150 milliseconds minimum. So what's the implication? So 150 millisecond ping time sucks, right? Like if you've ever played an online game with 150 millisecond ping time, it's no good. There's lag and there's glitches and you're jumping around. So that's not going to work for the real-time multiplayer aspect of a game like this. But we do want it to be global. So how are we going to do this in a way that we can kind of get this best of both worlds? So starting with the game server piece first, straightforward. We're going to aim to put game servers as close to our end users as possible. This makes sense, right? We're going to use AWS regions in Oregon and Frankfurt, new region we just launched, Tokyo, and then Brazil in order to get game servers as close to people as possible. But what we can't do is just kind of replicate data everywhere. Now, that seems like the easy way out. Like you just kind of connect all these regions and you build this big data mesh. Strongly recommend not to do that. And there's a few reasons why I say that. First of all, it adds all that latency right back into the system. So, okay, you don't have game server latency to your player anymore, but now you have a huge amount of latency in this giant data mesh. And you're talking about waiting 100 milliseconds and another 100 milliseconds and another 100 milliseconds. And if you're really trying to have any kind of transactional integrity, you've got to wait for that whole cycle to complete for any important transaction. Anything where it's like a purchase or anything and you want to make sure that the data is consistent, you've got to wait 400 or 500 milliseconds. Doesn't really buy us much from latency. And then it also adds a ton of fragility. Now, all of our regions are dependent on one another. It's conceivable that if you had a region in Brazil, for example, and that region had some issue, it could cascade through your whole environment and take everybody offline. Not what you want to do, not leveraging AWS to its fullest. So let's look at some alternatives. The first step is to take the old school concept of a game server. The Quake 2 days, like if you remember the old Doom server, like where it was the game server and you would connect and you would get everything from that game server and do all your gameplay and then disconnect. So we're going to take that and just kind of throw that on the ground, break it into a million pieces. And as we're picking it up, we're going to sort it out based on what our low latency pieces are and which pieces can deal with a bit higher latency. And when you do this, you come to a couple reasonable conclusions. Probably some of you have already been through this thought exercise as well. But first one, low latency game servers need to be next to players. You need that low 20, 50 millisecond ping in order to give people that real-time experience. But there's a whole lot of other stuff like auth and login, friends lists, leaderboards, all those kinds of operations. We're going to build those as a set of HTTP APIs. And what that's going to let us do is then deploy these different APIs around the world in different places where they make the most sense. So we're not just going to build one giant API stack. We're actually going to peel it apart and deploy these different API stacks around the world, which we'll talk about. One note, those of you who have been doing game server programming for a while might look at HTTP and say, no, we're more advanced. We know that we're going to need TCP sockets for certain kinds of things. We want a two-way bidirectional socket. We understand the trade-offs, so we're not going to get to take advantage of things like auto-scaling. And that's fine. If you understand those trade-offs, go for it. Again, the point of this is to just outline the thought process. So when you're deciding where you're going to deploy services where and how to connect them all together, you're able to leverage the most out of what AWS provides and then get the best experience for your players. It's obviously what we want. And another key point, I've got 3 more here. So any kind of data replication is bad, okay, right? Like we don't want to just build this big mesh. I already talked about that. It's going to slow everything down, add fragility. But local caches are good instead. So if you have a player's data and say I log in and my account's usually in North America, but I want to play against somebody in Brazil, it's fine to pull over a copy of the player data that you need while I'm running on that game server in Brazil, cache it locally. In fact, that's a very good pattern to do. And then when you're done with that, sync that back to a user's home region. And that brings me to my last point, which is nobody really plays everywhere. Like anytime I hear this, I'm always, a little alarm bell goes off that maybe the feature's a little half-baked. Let me tell you what I mean. So say I'm sitting around some Tuesday afternoon. I got time between meetings. I would never do this, by the way, but I want to play a few, rounds, maybe Knights versus Samurai, similar game, hack some people to death, and then before my next meeting. And so in this hypothetical situation, do I really want to go online and say, hey, find me a 4v4 deathmatch and go? And I say, hey, you're lucky. We've got a server for you right here down in Brazil. Enjoy. Like, no, I don't want that. Like, the latency is going to suck. And more important, I don't even know how to swear in Portuguese. So how am I going to understand what the guy is saying to me as he's laughing at my dead and decrepit body? By the way, I said I love playing these games. Doesn't mean I'm any good at them. I have lost my Thatch Twist responses long ago. But so when you talk about, OK, we want people to have this global experience, really what you're talking about is you want the ability for people to make that choice in specific situations to join other regions. That's very different than just magically having your data available everywhere and just randomly connecting to a region. It actually opens up a lot of possibilities for you as server architects to design your stack in a way, and we'll talk about this, so that when people actually connect and they say, OK, I want to play against my friend in Tokyo, you can have a person then transition between the different services you're building, have that game, and then still keep the majority of a player's data in their home region. Because the vast, vast majority of the time, people are playing in their home region. I'm playing in North America. That's where all my friends live. They're in the same time zone. We all speak the same language. Occasionally, I see them in the real world. It still exists for now. So that's where I'm spending most of my time. But maybe I'm up late or up early, and I want to play with somebody across the ocean, maybe a friend in Japan. That's a rare situation, so we want to support that. But we don't need to replicate all of our data to make that happen. So if we follow this kind of to its logical conclusion, what we wind up with is these loosely coupled pods that we can then deploy all over the world. And this is a simplified diagram, but the idea behind this is that you would have a set of web API stacks, or maybe something TCP if your game needs that bidirectional communication. But you've got these pieces of your API stack that are doing things like auth and login, just leaderboards, matchmaking. And that would be the stack that's in Virginia in this diagram. And then for game servers, you can deploy these around the world. You can Frankfurt, Oregon, Tokyo, et cetera, as we talked about. And this gives you a good separation of your different concerns because, again, you can have people contact your API stack, figure out then where they want to play, and you're still able to home your data to a person's home region. And last thing, I'll just, as a mental thing, I try to think of these as these kind of like little escape pods, like spaceship escape pods. If you think about Star Wars, the real first one where C-3PO and R2 blast off, they're kind of all independent, and they're getting away from the Empire, and you can have these space pods that can certainly communicate, which we'll show, but they're not dependent on one another. Again, if something in Brazil explodes, the other ones they just kind of keep going. So Martin gave a great talk yesterday about the web API stack, and it's a common pattern too, so I won't dwell a lot on it. But just to illustrate the point, this is what these API services that we're going to build are using. This is kind of bread and butter AWS. We're using multiple availability zones. We're going to have an auto-scaling group for our web tier that's going to live behind an ELB. We're going to have a caching tier. Elasticache supports both Redis and Memcache. Redis is very popular for game companies because it lets you do in-memory sorting and a lot of other more interesting operations than just key values. And then finally, Dynamo. I won't spend a lot of time, but I do just want to mention, I've had a lot of cases where game companies start out with a relational database, really push it past its limits, and move over to Dynamo. Dynamo is very well suited for games. So I highlighted here in this presentation especially. It can keep up with the right throughput. Common web apps are typically 10-to-1 reads to writes. Games are commonly 3 to 5x writes to reads, which means you're doing 3 or 5 times as many writes versus reads, which is a little bit insane when you think about it. But relational databases just really aren't built to withstand that. So EA gave a great example earlier where they moved from MySQL to DynamoDB, saved a ton of money, and also got much better performance. So please do take a look at it. And the last details on this stack would be users coming in, making HTTP requests. Any kind of content, static content, is going to go through S3 CloudFront. Pretty straightforward. And then finally, anything that can be processed just maybe a second or so later, put that in a queue, have a set of background workers take care of that. For example, I upload a new custom avatar, want to resize it, stick that into a queue like SQS, have a background worker pick that up, resize it, stick that in Dynamo or S3 or wherever that's going to go. Maybe beating somebody on a leaderboard, wanting to set out an alert, anything like that. Anything where you can decouple and put it in a queue. If it doesn't have to happen right now, put it in a queue, deal with it, a second or two later. Still going to have a very lively feeling system. And if you do that, then when we start talking about, OK, what are ways that these different pods can communicate, well, you can use these queues then to shuttle information between these different pods. And it's much better than having a tightly coupled database link between all of your different escape pods all around the world, because you're just going to forget which data piece is dependent on which. It happens time and time again, easy mistakes. But if you put it in queues, then you can see which data is flowing, and it makes it much easier to not only keep them decoupled, but also to understand how your application data flow is working. So let's walk through an example of this in action. I want to play Knights versus Samurai. I log in. It's going to go to my API stack. I'm going to download any updates. Maybe there's new items, new weapons, et cetera. And then I'm going to do matchmaking and say, hey, I want to play this kind of game. I want to play 2 versus 2. First team to 10 kills wins. And it says, hey, you're in luck. There's a game server right over here for you. And at that point then, my game client is going to make a direct connection to the game server. Could be a combination of TCP, UDP. Typically UDP for game traffic, as you're no doubt aware, because it gives you lowest latency. And if you lose a few packets here and there with UDP, it's not a big deal because you're just sending out this constant stream of updates. So gameplay is continuing, and I'm hacking my friend to death. I'm running around, and essentially, friend jumps in the game, still doing my real-time gameplay. And as events are happening, then I can still communicate with that main stack. And for example, when game over, report back my state at the end. So as I said, this gives you the best decoupling of different concerns in your stack. This example also gives a little bit of a simplified version where it implies that, okay, you start a game and then you move over to your game server and you move back. But there's no reason why you wouldn't have, in real life, both of those channels operating at the same time. So let me give you an example. For this, I've created a visual aid. OK, so you first log in. You say, OK, hey, I'm logging in. I'd like to play this type of game. I'm making my API requests. Give me, let me do matchmaking. It says, hey, you're in luck. Here's a server over here. So I say, OK, so I start running around. And I'm attacking my friends. I'm hacking them to death. I slice. OK, save that as an API. Oh, picked up 300 gold. Save that. Oh, hey, katana. Cool. Save that. Oh, I died. OK, I'm back in the game. OK, game's over. Send my final stats. And you're back out at the front. And you say, OK, that was fun. I want to play this kind of game, again, via API requests. Now I want to play over in Brazil. It hands me off to then a server cluster down in Brazil. I start my running around, and the cycle completes. So I'm going to stop there, and we're going to classify that as game developer exercise for the day. So you can have these two channels. And the thing that I want to emphasize is that this HTTP channel doesn't just have to be to one place. The benefit of these service pods, the service-oriented architecture, when you pursue it, and you say, OK, we're going to break these services apart. We're going to have an auth service. We're going to have a leaderboard service. We're going to have a matchmaking service. As these can live wherever. You can make a request to your auth service, and that could be maybe a central auth service, which is common a lot of times, especially bigger game studios. You have some kind of central authentication mechanism. But then you can make an HTTP request that's just as easy to make over to a local matchmaking service in, say, North America, or say down in Brazil. So it gives you a lot of flexibility there by breaking these services apart to be able to locate them where they make the most sense. Let's get into a little bit more detail then. We talked about what the game API looks like. Let's dig into what the actual game servers look like. Again, best practices, multiple availability zones for fault tolerance. We're going to create VPC public subnets. Again, no load balancer here. We're going to directly connect to the public IPs. And then we're going to spin up these groups of instances. And this is how our actual gameplay is going to happen. The game client is going to come in and directly contact our public IPs. And that's where all of the gameplay is going to happen. Have a private subnet for our data pieces, which could include a local cache. Again, for performance, you can pull over the data you need while you're doing your gameplay. And then last kind of critical component here is usually you're going to want some way for these game servers to communicate with one another. Let me give you an example. Let's say you're creating a world, like maybe an MMO world, and it's bigger than fits on one given game server. Or otherwise, you want to create this experience where people can kind of move throughout the world. And you need to send updates across your player population. Maybe a given server only handles maybe 32 people or 50 people, just depending on your architecture of your game server. And you want to send updates across all of your players. So you need some way to route messages between these servers. In a data center, a lot of times the historical methodology here was to put them all on a private switch and use multicast. Doesn't really work in a cloud environment, but luckily there are newer solutions that are just as good, if not better, because they give you a lot of extra features. So the de facto standard with gaming these days is using RabbitMQ for this. So RabbitMQ has an active-active mode. It's straightforward to set up. It runs on top of EC2 very easily. And then you can actually put ELB running in TCP mode in front of this. And I actually owe this tip to a game developer who we've worked with, because previously we were actually recommending people to use elastic IPs, but after some testing, turns out that ELB in TCP mode works really well. When you set it up this way, then your game servers can just connect to the ELB. ELB is going to load balance them somewhere in that RabbitMQ cluster. And then any kind of broadcast messages, maybe you want to send chat to a common channel, or maybe you want to send a game invite across, or maybe you want to send an announcement. Any of that kind of traffic can go straight across that RabbitMQ cluster. And RabbitMQ is a great fit for this because it's very low latency, a couple milliseconds latency. Again, easy to set up, and it kind of just works. One caveat I'll mention, and then I'm going to go into a few more details on RabbitMQ. One caveat I will mention is that actually making a do-it-yourself clustered queue like RabbitMQ durable takes a good amount of work. So while this setup is really good for transient messages, that maybe if you lose a few now and then because a node crashes, not a big deal. Like if you lose some chat, like nobody really cares. Like that happens all the time, right? IM drops messages all the time. You're like, hey, dude, are you there? Yeah. Oh, yeah, whatever. So that is fine, but you really don't want to set up your own queue to necessarily transport crucial transactional, like purchase information, unless you're going to invest time in using our services like EBS, really investigate durability, backup, snapshotting, et cetera. I'm not covering that. I'm covering more the simple use case where you can just use to transport that low latency data between your game servers. And again, your game players are coming in, playing on a server. This is all part of that experience. And then as I mentioned, anything that you want to either process in the background or possibly transport to another pod, you can use a queue, either RabbitMQ or that's a generic queue icon. You could also use SQS in order to transport that between your different pods. I just put this in. You can read this later, but make sure to enable enhanced networking. And for any kind of game server, it makes a huge night and day difference. These slides will be made available, and those are just some links to help you out. So back to RabbitMQ, what does it actually look like? So we spin up 2 nodes. As mentioned, we connect a TCP mode elastic load balancer in front of them, open up a few security ports so that it can do replication. And then there's a couple little funny things about RabbitMQ. You actually need to assign local host names because that's how it actually sets up the databases. So if you just use whatever random private IP address that EC2 assigns you, and you stop the node and you start it up again, you get a nice, freshly wiped, no queue available, totally. I've never been part of any cluster before, RabbitMQ node, which is probably not so much what you want. But if you follow the steps here, again, this is stuff you can read later. These slides will be available. RabbitMQ docs actually have a really good walkthrough on this, and then I put just some additional notes in terms of which ports to actually open up. If you follow these steps, what you wind up with is a configuration file. It looks something like this. It's got your 2 nodes in it and your port you're listening on. So I'm going to mention one alternative, and then I'm going to come back to this, and I'm going to talk a little bit about automation. One alternative to RabbitMQ, just worth mentioning, is if you're using Elasticache, and you're using Elasticache with Redis, Redis has a pub sub mode too, which works great for this purpose. You might be able to simplify your architecture by just using that and using the Redis pub sub capabilities. Similar failure modes to RabbitMQ. If a node fails over, Elasticache for Redis has auto failover. If a node fails over, it's possible to lose a few messages. Again, for non-critical data, not really a big deal, but just keep it in mind. So back to RabbitMQ. All that kind of configuration is fine if we want to do it manually, but really nobody wants to do that manually. It's fine if you're setting it up for dev. But if we're talking about really pursuing this and having, hey, all of these different pods all around the world, we're talking about, hey, we're going to have 10 or 20 of these, and then we're going to have all our microservice stacks. That's a lot of stuff to do by hand. We don't want to do that. So the winning kind of combination here that's very popular with game companies and non-game companies alike is using CloudFormation and Chef. CloudFormation is great for automating the AWS pieces of it, setting up your VPC subnets, setting up all your security groups, and so forth. And then Chef comes in at the part where you're saying, OK, well, once these nodes come up, I need to actually join them together, assign them host names, make them aware of each other. All of that stuff that happens at that application level, that's where Chef is really a perfect fit. OK, so with that, I'm going to switch over to the live demo, see if this works. Now, what I'm going to show you guys is actually something I'm pretty excited about. This is something we've been working on in conjunction with Epic Games. So I mentioned using Chef for RabbitMQ. With another thing, when you talk about spinning up these game servers, is how do you actually automate a game server? So what I have here is a series of CloudFormation and Chef recipes that together will actually launch an Unreal Engine server in actually just a few clicks. And this is something that Nick Downs, another member of my team, put together. Did a heck of a lot of heavy lifting here. If you look down here, you see the JSON. These are our actual template files that go into CloudFormation. Here's a TGZ of our Chef recipes, our Chef cookbooks. And then finally, there's your actual Unreal Engine server. All right. So with all that in mind, then, all I need to do is run a simple AWS CloudFormation command, and then it returns me back a stack ID. Now, like any good sleight of hand artist, what I'm going to do is I'm going to switch over. I can use this then to monitor the the status of it. I'm going to switch over then to look at one that I've already created previously, because it takes a few minutes to boot up. So this is in the CloudFormation console. And if I look through here, I can actually see that, OK, the CloudFormation stack completed. And when it gives me the outputs, then I can actually get the IP. This is the server IP, then running my Unreal Engine server. Oops. Now I can connect to it, theoretically, if the Wi-Fi works. All right. And a little bit of Linuxy goodness. And now I can see that Unreal Engine is running in the background here. So if you can see that in the back, you can see it's just a process running. So we're going to open source this, which is actually pretty exciting from my perspective. We've been trying to do this for a while now, and we finally are able to do it. So keep an eye on this. We're going to be releasing this open source, and then you'll be able to download this template and then modify it, change it, maybe if you need to change the number of servers or where they're spinning up, et cetera. But at least get you started and get you up and running quickly. OK, so a few more notes, and then I'm going to hand it over to James. This is just a recap. This was the command I ran. This is what we saw when we went into the console. We got the IP address, and then we were able to connect to it and actually see Unreal Engine up and running. OK, last thing I'm going to talk about is server registration. So where are my servers at? Sorry, I couldn't resist. Cheap joke. So far, we've talked about these pods, and they're all independent, and they're running around, which is cool. But they're all decoupled, but they're actually kind of non-coupled, right? Like right now, they actually don't know about each other whatsoever. So if I've got this nice little matchmaking service that's running here, and I want to connect to it, how is it going to know even where the servers are located? How is it even going to know that these pods exist? And this brings about the concept of server registration. So we're going to have this matchmaking service. And as our servers spin up, then using, for example, the CloudFormation and Chef template just showed you, they're going to send a request using the same API we just built, HTTPS, obviously. You'll want to secure it with some kind of unique key. Glad to discuss that as a sidebar later, but that's pretty straightforward. And then as your different servers spin up, they're going to basically register, and they're going to be sending a heartbeat. They're going to say, OK, I'm up. Here's my public IP. Here's a number of people on my server. I can accept 4 more people. And they're just going to be sending that every 30 seconds or whatever makes sense for your game. And then that's going into a DynamoDB table that has your server list. So through the same service then, your game players can actually come in and say, OK, I want to join a server. And it says, hey, you're in luck. Here's the list. I know there's spots playing this game mode on this server right now. Returns back the public IP. And then the game client can actually transition and connect to that public IP and do that whole sequence we talked about earlier. And the second part of it, the last part of it, is you have this background job running that's watching that table and just looking to see if any of the servers have gone unhealthy. So it's just running on a timer, doing a little cleanup loop and saying, uh-oh, I haven't heard from this server in 3 minutes or 5 minutes, whatever makes sense again for your game. Maybe it's time to at least put it in kind of an unhealthy state. Similar to what ELB would do, but again, game servers, they need a little bit of custom logic here because game servers aren't just all interchangeable. You can't just randomly kill one at whim. Everybody will get kicked off. They'll get all pissed off. They'll start flaming you on the forums. You'll learn all the new insults of the week. But kind of trying to avoid that, right? OK, so you've got this cleanup loop. And then the last part is you say, OK, we're running low on capacity. Turns out we actually need some extra game servers. Just make an API request out and say, OK, spin these up. Use that template. Spin another one up. Spin it in this region. It comes up. It registers. And that cycle continues. A few odds and ends. Just an example of what you could do. HTTP post. Highly recommend you include an HMAC. Very straightforward. It's like a double SHA-1 or SHA-2 of the actual payload along with a custom salt. It's straightforward stuff. And glad to discuss that in details if you want. And then sending that server status, as I mentioned, then you have that background job that's monitoring it. And the 2 last details before I hand it over to James, who's going to give a real-world example of following these kinds of patterns with Loadout. Understanding how your game servers are running, pretty important, like are they performing well or not. 2 ways to get game server logs off. One of them is CloudWatch logs. Bone's simple to get started. Just configure it. You can install the agent on all of your different instances and push those logs to your S3 bucket. And then the other pattern that's emerging more and more is people actually using Kinesis. Now, between these 2 patterns, I wouldn't say one is clearly better. they're just they're good at different things. CloudWatch Logs is great if you just want a way to collect your game server logs, if you're going to do like postmortems and you want to do debugging, and you just want to stick it in an S3 bucket and then process it in batch later. CloudWatch Logs is great for that, super cheap, simple to set up. But if you say, hey, we want to actually alert in more real time, maybe build a dashboard on which players are building which games and how they're doing, that's where using something like Kinesis can buy you certain advantages. And Kinesis specifically has a plugin now for FluentD, which can just run like an agent on your actual game server or on any of your servers, really. There's nothing game server specific about it. It can just run there, collect whatever metrics you want, shuttle those to Kinesis, and then you can still put them in S3 if you want to just dump a copy for later, so however you want to comb through it. And then you can also do things like send it to Redshift or send it to a live dashboard that you've built on top of maybe Dynamo or EC2. So it just gives you more flexibility. And final thought to drive this architecture home is, China obviously has certain specific challenges because of the fact that it's kind of separated from a network perspective. And the good news is that if you follow this architecture pattern, you say, OK, we're really going to break things up into services. We're going to have people's data by where they predominantly play. And we're still going to want to create this community, this global community. You can achieve it then. You can have these regional pods where people's data lives. So that's where they play the vast, vast majority of the time. And then if you want to do something like create a global leaderboard and say, hey, we want a leaderboard that shows everybody around the world, US, Europe, China in one place, then you can create a web service that just does that, purpose-built, and you can deploy that in the region that makes sense. So with that, I'm going to turn it over to James, talk about the architecture for PlayFab for Loadout.
Well, thanks a lot.
Cool.
And I'd really say, sitting through Nate's conversation, it's really uncanny. Because so much of the architecture I'm about to show you follows exactly the same patterns Nate just spoke about, and yet we had not coordinated prior to doing this talk together. So obviously what he's saying must be completely correct because we're doing the exact same thing, and obviously we're doing the right thing. So what is PlayFab? So we have built essentially a platform as a service for gaming. And so if you wanted to do, for example, everything Nate was just showing, but you didn't actually want to build it yourself from scratch, PlayFab is an option you can look into. And essentially what we've got is three things. We've got tools you can use for actually operating and maintaining your game in real time. We've got all these cloud-based backend services, all accessible via a web-based API, and we call that kind of our backend services. And finally, we have an ecosystem of a bunch of third-party services that are sort of already pre-integrated into the system and more to come. So for example, we've done a deal with Photon to integrate the Photon multiplayer server in, and that'll become tighter and tighter integrated over time. But what I'm here to talk about today, in particular, is Loadout. And Loadout is a first-person shooter. It's a free-to-play first-person shooter developed by the Austin studio Edge of Reality. They built this game using PlayFab. And so we essentially have built and are hosting all the back-end services for them. And we're also hosting their game servers around the world. So they built their own game server. They built their own game client. And then what we're doing is we're doing the work of exactly what Nate described, having these regions and pods around the world where we can take those game servers from them and move them around. And I'm going to talk about a bunch of sort of patterns and tips and tricks we followed. And if I have time at the end, I'll actually show you the tool and show you how easy it is to actually upload a build and choose which region you want the build to go live in and do it that way. So some quick stats. I mean, Loadout's been live now since January. We've logged over 1 billion API calls in our system from it. At the peak, we had about 300,000 DAU, and at its peak and launch, we had 120 sort of dedicated servers that we were releasing from SoftLayer, and we had 110 EC2 instances spin up automatically to handle overload or overflow for bursting, which is exactly what they're there for, and it's great to have that sort of capacity available. In building PlayFab, some tenants we followed. We never wanted any scheduled downtime, so everything we built was designed to be able to bring up a new instance, get all the service switched over to that, and then take down the old instance, so you never had these, it's 11 p.m. and you can't play your game because they're upgrading the servers, automatic scaling using Elastic Beanstalk, and then again, developers should not need to know what's going on behind the scenes. So once you have a clean API, you can do whatever you want behind the scenes. And a good example is that we originally were using SimpleDB for a lot of our databases. Over the last couple months, we have switched everything over now to DynamoDB, which is fantastic. And none of our customers have noticed anything because they don't need to know anything. It's all going through APIs, and they don't know what's going on behind the scenes. And finally, this buffering comment. When you have a lot of tightly coupled servers, you think about it like expansion joints on a bridge. If you've got a lot of tightly coupled servers, and one of them suddenly has a temporary slowdown or a lag or something, if they're too tightly coupled, that can ripple through the whole system, and that's really bad. So you want to have, wherever you can, wherever you have servers talking to each other, have some buffering in there, so that if this thing suddenly temporarily is down, things don't just all grind to a halt. They just kind of queue up, and eventually they release when that comes through. So we'll talk about that in a second. So let's look at our architecture. So so our architecture follows exactly what Nate described. We have a whole bunch of HTTP-based web services, and then we also have a whole bunch of game servers around the world. So this is basically the web services stack of our system. So we have the game client. We're using Route 53, and what we've done is every game on our platform has its own URL. And that's really nice because it means that we can have the URL mapped to one IP address, or we can, for example, if we wanted to give a game its own completely independent set of hardware, we can simply use Route 53 to map that to a different set of hardware. So every game has its own endpoint. It goes into ELB for load balancing. It goes to one or more web servers to handle the load. These web servers are in different availability zones, so we can handle outages. And then we're using all this suite of services in the background. And then the multiplayer game server side, again, similar pattern. We have the notion of a matchmaker, which knows about all the different servers that are out there in the world. We have the notion of a game server monitor, which is periodically pinging servers to make sure they're all healthy. And then we have on the top right, what you're seeing is EC2 instances being spun up in different regions. And in the bottom right, we have dedicated hardware that are sort of leased servers that we're leasing from an Arceus software, but it could be other providers around the world. This is an example of the kind of web APIs that we have in our system. Obviously, I know you probably can't read all these. My point here is simply that there's a bunch of different kinds of services on there. We have one client API, which is inherently non-trusted. You can't trust your client because people can hack their clients. So we don't, for example, allow our clients to simply say, give me 1,000 gold pieces, or give me the sword of Damocles or something, because you could easily hack that message, especially when you're using HTTP posting as your primary protocol. So the client API is things like get catalog items, do this transaction, store this property from our user. The server side is things like give me a gold, give me an item, more declarative things, because our server API is trusted and with the client server API is not trusted. A typical API looks like this. So this is an example of a matchmaking request. So the client is passing in a session key for authentication, and it's basically saying, matchmake me against this build version in this region, in this game mode, in this lobby. And then the server basically responds back saying, great, here's your lobby ID, here's the IP address to connect to, here's your port number to connect to, here's your security ticket. And then the client can take that information and then make its own separate connection request directly to the game server to begin the game instance. And that's an example of how you might use the web API to set up the connection, and then you go directly to the game server for the actual gameplay itself. Now I'm going to show you some sort of tips and tricks we've accumulated along the way for performance reasons. So one of these is the notion of using the actual ELB itself for logging purposes. So we wanted to have a log of every single API request made and by which game. And it turned out the most efficient way to do this was to simply have the ELB log itself get dumped out and then process that in order to generate those API logs. So what's happening here again, this is an example of a login request. So my game client is connecting up to Route 53 and saying, basically, I want to log in. And it's going here against 3.playfabapi.com. That means I'm connecting to game number 3. That's how I know that this API is for that particular game. And then what can happen is we're now able to grab those logs that get dumped into S3. We have a report service that analyzes those logs, puts them on the Redshift. A typical log event looks like what you're seeing there, the user ID, the event name, and so forth. And all of that can then go into Amazon Redshift for analysis. And here's an example of an API usage report that might get dumped out. So we can see, OK, the user info request was called 93 million times, for example. So that's an example of a report we look at a lot to see what's going on under the covers. Another pattern that we find very useful, this notion of when you have a singleton service. So the reason we have a matchmaker, we wanted to have one matchmaker service that essentially has in memory all the different game server instances around the world, because it's very convenient to have all that in one server. This is an example of something you don't want to shard out. You want to have one box that sort of knows about all your different servers, but obviously you want to make sure it's highly available. So what do? So the answer is you have two instances in different availability zones, a primary and a secondary. And in this case, what we're doing is we're using basic Elastic Beanstalk to basically keep an eye on these two instances. And if one of them, the primary in this case, goes down, then ls beans I can note about that, terminate it. Route 53 independently is also set up to be doing kind of health checking. When Route 53 notices that the primary is down, it will automatically shift over to the secondary and start using the secondary for all requests. Meanwhile, the autoscaling is going to have noticed that the primary shut down. It will automatically restart the primary, and then eventually, once it's back up again, it will switch back over again. So that's an example of a pattern using 2 different services for high availability on a singleton. Another thing we do, server health, really, really important. If there are problems, you want to know about them as soon as possible. We use a couple different things to keep track of all the different servers in our clusters. So we use VictorOps as the service to basically gather information from CloudWatch and do things like send out pager notifications and make SMS messages and phone calls at 3 a.m. to tell people that there's a problem. Separately, we use a third-party service, Pingdom, which is basically just doing a very simple pinging of all different servers in a system on a regular basis to get sort of an independent health check of what's up, what's down, and that's proven to be a pretty effective system. Another thing we talked about is buffering. Here's an example where we do logging not of kind of APIs, but we have a whole bunch of custom in-game event logging we do. And so one thing that's very nice is when you have an EC2, you can set it up to automatically get a local SSD drive. And that is not something you want to use for long-term data storage, because as soon as that EC2 instance goes away, you lose your disk storage. But it's perfect for caching local data. So you can cache all your events on your local drive, and then you can have a service pick up those logs from time to time and shove them over into Redshift for processing. And we're doing that both on local event logs, things like sort of standard error out type logs, as well as actual kind of server logic logs, which in our case get a little bit more fancier analysis. And actually here we're using RabbitMQ, just like we were describing earlier, to do that analysis. So again, very common pattern. Again, lots of different storage mechanisms. DynamoDB, we use RDS, we use S3, different systems for different things. If you look at what we're doing with the DynamoDB, it's really good at player data because we don't have to worry about sharding. It's it's highly available. We're able to store things in here like the user data, custom properties, inventory, and using, in this case, pretty commonly the primary hash is the user ID, and then the secondary hash is going to be things, or the range key is going to be things like your item or your title to get at just the data for that particular player. Physical deployment, common scenario, we have, just like we were describing, pods around the world, but all of our core services live in Oregon. That's where our primary kind of main services live. We did start originally over in US 1, and then we basically moved it to US West 2. And what's interesting about that is when you have a system where you have you're moving from one data center to another data center, you've got this problem. You have all this data here. Now you want to move it all here, and yet you don't want to shut everything down and sort of copy everything over. And it's too much data to copy on the fly. So one very common pattern is to have logic to dynamically know about the possibility of multiple places. So we wrote this code. You probably can't read it, but what it basically says is, I know that a player's data may be in 2 different places. And I'm going to, by default, look for it here. And if I don't find it here, I am going to automatically fail over and look for it here. And if I find it here, I will then read it in, and then when it's time to make my write, I will write it back to the first place. And that's a common pattern you can set up, and that's useful for all sorts of things like data migration, multiple data regions, that kind of thing. OK, I'm going to give a really, really, really quick demo, if I can, and then we will take a break. Oh, I need you to log in, Nate. Sorry. OK, so a couple different things here really briefly. So one of the fun things to look at is in our system, we're logging, for example, every time a multiplayer game session completes, we automatically create a log file from that server instance. So I can pick any one of these game sessions here, click the log button, and I'm getting a copy here of my actual server log. So that's a perfect example of what we're doing. After the game session ends, that log file gets shoved over into S3 for archive purposes, and then you can index them and research them and use them for debugging and so on. So that's one kind of neat little pattern. This is our actual tool itself. And so you can do things like see the dashboard for your game, do things like go into your catalog management. And for example, if you're managing in-game inventory, here's a card from a card game, and you can set properties on this card and so on. What I want to show you is server management. So going back to what we're describing just now, you've got this pattern where you want to be able to upload game servers around the world. So in our system, you can actually go in, find your actual game server, which is just executable, which knows how to run. It could be an Unreal server instance. It could be your custom game server instance. Give it a name like AWS demo, hit submit, what it's doing is actually uploading that zip file now to the server, and it's basically now going to sort of unpack that zip file. And now here it is. This is the one I just uploaded, and this is now available. And I could actually go in right now and simply say, I want that available to be in US Central, US East, and Japan, and hit save. And this system is going to go now and do exactly what I described earlier. It's now going to automatically in the background spin up EC2 instances in those 3 different regions. It's going to copy the executable over. It's going to get it all unpacked and set up and create a custom AMI for it, get the AMI all configured. And then the matchmaker now knows to go and connect to those servers and start things running, which is pretty cool. So later, when I go into servers, it's not going to show anything. You can see right here, these 2 are now initializing. They're not live yet. It's going to take a few minutes to get those spun up and running. But that's an example of the kind of benefit of of following this pattern. And in our case, with an off-the-shelf tool that does it all for you. So with that, I think we're done. I'm happy to talk to you more about the stuff of how we chose to implement these patterns in building PlayFab. Or if you're interested, we'd love to talk to you about using PlayFab for yourselves. So with that, thank you very much. I think we are done.